Up here to see if we can remember how these two elements would come together. What kind of a compound are they forming when they come together? What kind of a compound? What were our kinds of compounds that we've introduced so far? Molecular and ionic. Is this a molecular or ionic compound? Ionic. How can we tell? It contains a metal, right? And for now, when metals form compounds, those will be ionic compounds. What was another name that we gave for compounds that are ionic compounds? We said we could also call all of these compounds salts. Salts. Very good. So, see if your partner remembers this. How can these two elements come together to form a compound? All right? Talk to them, see what they know. Anybody need more time? Raise your hand if you need more time. Nobody needs more time? Everybody's got it? Excellent. Okay, so then, what's the right answer? C. So how did we know that? How did we know that? We looked at potassium. We looked at oxygen. We knew that they were going to form an ionic compound. Now, we've said that one way that we can identify an ionic compound is by seeing that there's a metal in the compound. But the strict definition of an ionic compound was a compound made of what? Ions, right? A compound made of ions is an ionic compound. So we know that these are going to form ions. And once we know that, we can look at where they're at on the periodic table, and perhaps that will tell us the kinds of ions they want to form. What kind of an ion does potassium want to be? All right. It wants, well, argon actually, correct? Yeah. It wants to have an electron configuration similar to that of argon, and to do that, it needs to, what, gain or lose electrons? Lose. How many? One. So when potassium loses an electron, what results? What do we call that? A potassium ion, right? This is now a potassium ion. And it has a positive charge because now it's given up an electron. So that's what potassium, that's the kind of chemistry potassium likes to perform. It likes to release an electron, right? So this goes into this, where this electron comes off and you're left with that ion. All right? What kind of chemistry does an oxygen atom like to do? It wants to what? Gain 2 electrons. So it would like to take 2 electrons, add them to it, and the result would be what? With a 2- charge, correct? An oxygen ion, or the oxide ion. All right, so then we see that these are the ions that these elements want to form. K plus, O2 and you can do this little thing here, and you can say it must be K2O. All right, everybody remember going over this last class, or have some recollection of this somewhere in their learning? Great. Here's another one. Talk to your neighbor, see what they know about this one. Did everybody get a periodic table from me? Does anybody else need a periodic table so they can see it close? Yeah. I think I have one here. Oh, you have one already? Okay. Okay, how about this one? What's the answer to this one? C? All right, very good. Okay. Excellent. Now, for our representative elements, and which elements up here are our representative elements? First two and last six, and really just the ones to the right of the staircase on the last six. But in there, we can predict the kinds of ions that those elements like to form. However, elements in our transition metals and post-transition metals are not as easily predicted, the kinds of charges that they'd like to form, simply by looking at the periodic table. All right? So, for example, iron likes to form either a +2 ion or a +3 ion. In other words, it will find stability in compounds where it was allowed to lose 2 or lose 3 electrons. And if you look up on the periodic table, if iron loses 2 electrons, it'll have an electron configuration similar to that of chromium. If it loses 3, it'll be similar to vanadium, but those aren't noble gases, right? Or noble, yeah, those aren't noble elements. So it's not easily predicted what kinds of ions these transition elements will want to form. And again, it's also not always the same transition or same charge state. Sometimes it could be +2, +3. We have +1s in here, and sometimes you'll see +5, +6s, or +7s. So there's all sorts of charge states that elements might be forming if they're in the transition or post-transition metals. Okay? So we don't want to spend a whole lot of time kind of dwelling on the kinds of charges that they'll form. So I want to commit a whole lot of effort into memorizing this information. We'll talk about ways that you can kind of look at a compound and know the charge that's there. For example, if I have this compound here, what's the charge on my iron ion in this compound? Is it +2 or +3? +2, because what? The ions that chloride likes to form are what kind of a charge? -1. Does everybody know how we can see that from looking at the periodic table? All right, excellent. So because there's a ratio of 2 of these for every iron, right? That means the iron must be a +2 charge, right? So how about this one? What's the charge on the iron in this case here? +2, right? Because oxygen likes to form a -2 charge. All right, excellent. Very good. We also mentioned briefly that multiple elements can come together and result in a charged compound, which was an ion. It's not a compound, but it's an ion. Therefore, we call it a polyatomic ion. Polyatomic, many atoms, right, coming together to form an ion. And this is a list of the major polyatomic ions that exist out there. And this list is also available for your use on the back of your periodic table here. Okay? And there's multiple ways that professors can address using or learning these polyatomic ions. And my experience is I've had to memorize these multiple times for classes throughout my life. But I don't know, maybe my memory is not very good. But when I memorize things through flashcards and stuff, it doesn't stick very long, right? I find that if I need to memorize or learn something that I use frequently over and over, then that sticks in my memory a little bit better. So what I'm more interested in you doing is having this list always available to you when you're doing your homework or in class, and then when you come across a polyatomic ion, pulling it out, finding the name of the polyatomic ion and the charge that it has. And if you commit to doing that, not try to memorize them. You're welcome to try to memorize them for a test or whatever. But again, I don't think that's going to stick. If you commit to pulling it out every single time you come across one, you'll start to pile up all the experiences you need to have those well enough understood. Okay? So that's the way I want you to use this polyatomic chart. So here's an example of the kind of question where you might have to use the polyatomic chart to get an answer. So what is the name of this compound? All right. So we need to know the name of this polyatomic ion, right? We pull it up on our list, find its name. What's it called? Sulfate. Iron, so we say iron sulfate. Now, is this an iron with a +2 charge or an iron with a +3 charge? Did somebody say it? Has a +2 charge. How do we know? Because the sulfate has a what? A -2 charge, and it's a 1-to-1 ratio. So this isn't just iron sulfate, it's iron 2 sulfate. And again, the 2 is to indicate that there's a +2 charge on the iron. Could you tell me the chemical formula for iron 3 sulfate? What's the chemical formula for iron 3 sulfate? Why don't you write it down and explain to your partner how you know that that's the correct answer? And if you don't know, or if you do know and you want to pretend like you don't know, you can just ask them. Iron 3 sulfate. What does the 2 in iron 2 sulfate mean? The 2 means that that iron has a +2 charge on it, right? It's in the +2 charge state. So when we're interested in iron 3 sulfate, it means that the iron must have what kind of a charge? +3, right? So we're looking for a compound that's formed between an iron with a +3 charge and sulfate with a -2, right? And that should be Fe2SO4 3. Who got that? Raise your hand if you got that one. Okay, does that make sense though? Does everybody understand why? In this case, each iron has what kind of a charge on it? What's the charge on the irons here? +3. So we have Fe with a +3 charge. And there's 2 of them. Fe. And then how many of these sulfates? 3. What's the charge on the sulfate? SO4 2-, right? And these charges have to add up because when iron and sulfur and oxygen all came together, the iron gave some electrons to the sulfur and oxygen. The sulfur and oxygen took those electrons, but it has to be the same number, right? There weren't some electrons that just skirted off into Never Never Land. Every electron has to be somewhere around some proton or cluster of protons in polyatomic form. Okay? So this here, which is a total of a +6, has to be equal to the -6 there. Okay, should we try another one? So, what is the name of this compound? What's the name of that compound? So here's a chance for you to actually write down a word, right? The name of the compound. If you don't write it down, if you just told at the end, then you lose the opportunity to see how well you're understanding what's going on. So if you write it down, is it chromium phosphate? Is that right? Okay. If I told you I went to the store and bought you some chromium phosphate, what would you say? You might say, oh, thanks, that's very nice of you. But you would just be humoring me because you don't know what kind of chromium phosphate it is. Chromium is a what? What kind of element is it? Where is it at on the periodic table? Transition metal. So maybe I bought the wrong kind of chromium phosphate, right? It's possible because chromium comes in multiple charge states. So I could have bought chromium 2 phosphate, chromium 3 phosphate, chromium 5 phosphate, right? So what is this one here? Chromium 2 phosphate? 3 phosphate? What? 2, 3. So how do we know what the charge is on this chromium atom? How many are there for every phosphate? There's just one here, right? No numbers. So it's just one. One chromium. Some charge on that chromium. How many phosphates? 2. Right? We see the 2 there. What's the charge on the phosphate? Huh? -3. How in the world do you know it was a -3? That table, correct? So what's the charge on this? What does that mean? Must be a +6, right? So this is chromium 6. That's not 6.
Where does 6 come from?
I don't know.
We put it there.
Which 6? This one?
You wrote +6.
That one there?
Yeah, that one.
Okay. So how did I know that this was a +6? So first of all, we put a question mark there because we didn't know. Right? Do we know how we got these -3s? No? So once we saw that this was a polyatomic ion, we need to look at the polyatomic ion chart. And we want to look at the name of it and look at the charge on it. So this is phosphate ion, and it has a -3 charge. The chemical formula was this, right? This was provided, and the question was, what's the name of the compound? So we knew that there were 2 of these PO4 3 minuses. And we know that the resulting charge on this, which is what? What's the sum of those 2 charges? -6. Has to be on all the positive things. How many different positive things are there? There's just one, right? So this charge here has to be +6. So once we get that, then we can know that we have to name it chromium 6 phosphate. So if I go to the store and I say, I bought you some chromium 6 phosphate, what are you going to say? Thank you. That's right. Unless I bought the wrong thing. Maybe I was supposed to buy chromium 2 or chromium 3 or something like that, right? Okay. So we're learning how to name some compounds, right? Other ionic compounds that are made up of representative elements are really easy to name. Because, like this compound here, what's its name? Sodium chloride. Where did you guys learn that that was sodium chloride? Did I already talk to you about this, ask you this before? Most everybody knew that already from somewhere. Probably your grandpa. Or maybe your grandma. Always telling you what the names of elements are, compounds, right? Anyway, however you got it, you know it's sodium. That's the name of that. And then chloride. Notice it's not sodium chlorine, right? It has a little pattern there for us. And that's the pattern that we'll use to name all of our salts, all of our ionic compounds. So this is the one that we can go to and always remember what its name is, right? So here we go. What's this called? Tell your neighbor what the name of that compound is there. Here's another one. There's another one. So what do you got here? What's the name of this compound? Anybody know? Rubidium nitride. Rubidium nitride, right? We took nitrogen and turned it into nitride, just like we took chlorine and turned it into chloride. Okay, how about this one? Alp. Aluminum phosphide. What's phosphate? That was that business over there, right? Okay. And is there a phosphite on our thing or no? They don't have that on our list, but a phosphite exists as well. Okay, so aluminum phosphide. Phosphorus, phosphide. How about this one? Strontium bromide. Strontium bromide. Now, is this strontium 2 bromide or strontium 3 bromide? It's neither. It's just strontium bromide. Why is that? Why don't we have to call this one strontium 2 or strontium 3? Yeah.
Because it wants to become like proton and use 2 electrons, and bromide wants to get 1 electron, so we need 2 electrons.
Okay. And we can tell that because strontium is a representative element, right? It's not in the transition area where we will have to identify whether it's a +2, +3, +4. Okay? So if it's a transition if it's a transition element, you need to have some way of telling somebody else the charge on that element. But if it's just from the representative elements, you can tell from the periodic table the kind of charge that it's going to have. Does everybody follow that? Any questions about that? So this is all of these, strontium, rubidium, and aluminum, and let's talk a little bit about aluminum, are representative elements. Where's aluminum at in there? You see aluminum? It's element number what? 13. So it's still a representative element. It's kind of squirrely because you might say, wait a second, it's on that side. But can you see how it would like to form a +3 ion? Can you see that? I mean, if it's going to try to have an electron configuration like that of a noble gas, what are its options in terms of electrons? What can it do? Yeah, lose 3 or gain 5. And 3's easier to lose than gain 5. So aluminum is going to form a +3 ion. Okay, very good. Aluminum phosphide, strontium bromide. No strontium 2 bromide required, right? Okay. Molecular compounds. Molecular compounds. Also called covalent molecules. Okay, or molecular molecules. They have a different way of being named. And thankfully, you know one of these by their officially correct name, so you can use it for a pattern. Just like you know sodium chloride is a good model for naming what kinds of compounds? Ionic compounds. The model that you have for naming molecular compounds is this one. You guys know what that one's called? Carbon dioxide. Carbon dioxide. All right? And this one, does anybody know what this one's called? Carbon monoxide, where the mon in the di is indicating to you the number of oxygens. Is this an ionic compound, did we say? How can we tell it's not an ionic compound? No metals. No metals. So carbon and oxygen can come together in different ways, and we need a way to distinguish that. So we say carbon dioxide or carbon monoxide. All right? So here are two compounds, SO2, SO3. Following that model, is this a molecular compound or an ionic compound? Molecular. So it's going to follow this model of naming. What would you call that one then? Sulfur dioxide, right? Not sulfur dioxygen and not sulfur oxide, right? Because it's a molecular compound. This one here then would be sulfur trioxide. Very good. So we do need to have a little tiny itty-bitty conversation about our prefixes here and ways to remember them. Mono, di, and tri, I think, are pretty straightforward. Pentagon, hopefully over time you'll remember that that's a five-sided figure. Penta. Is there any other way to remember penta? What's that? Hexa, 6. Hexagon. All right. Hepta, not as easy to remember. Octa, 8. That's pretty straightforward. Nona, just like nano is our 9, and then deca is our 10. And remember how we had our conversation about the months? September, October, November, December. We had that conversation. Remember that? So hepta stems from the same prefix as septa in September. So that was our 7th month a long time ago. October, November, and December. So those are some ways that you can remember those. Tetra is really the only one that doesn't have something that I can lay claim to really easily for you guys. Anybody know a root that contains or where tetra could be tied into your memory? What? Tetra is 4. Tetrahedron, that was a word that we might have been introduced to in math. But there's a game called Tetris. Who's ever played Tetris? Anybody ever played Tetris? If you haven't played Tetris, Tetrus, I think it is? Ah, yes, Tetris. You should go home and play it so that you know, it's no fun anymore. It's all boring. But you could play it for a little bit so you'll remember. But in Tetris, there are little blocks that come down that always contain 4 units, right? Sometimes the 4 units are arranged differently. Sometimes they're like this, 1, 2, 3, 4. Sometimes it's 1, 2, 3, 4, right? Any kind of combination of 4 like that. Sometimes it's like this, 4 like that. Come falling down, and you try to line them up so that they make a nice level line on the bottom of your screen. And if you can line it up so that 4 rows will get all filled at once with one of these long skinny ones, right? Then what does the screen do? It flashes Tetris, Tetris, Tetris. All right? So it's talking about the 4 rows there. All right? So it's all about the number 4. So tetra is 4. Okay. So if I had this compound here, PF4, what's its name? Write it down and see if you show your neighbors. See if they get the same thing as you do. PF4. Here's another one. What's the name of this one? SCl6. Anybody got a name for this one? What's P? Phosphorus tetrafluoride. Very good. Phosphorus tetrafluoride. Should I write that down? Who wants me to write that down? Raise your hand. All right. Phosphorus tetrafluoride. Okay, how about this one? Sulfur hexachloride. Sulfur hexachloride. All right, excellent. How about the last one on this list? What's the name of that last one? Okay, so what do we do when there's two of the first thing? Did I hear dinitrogen? Is that right? Yeah, that's what we need to do. We need to say dinitrogen pentaoxide. Okay? And the other one's hydrogen chloride, phosphorus pentafluoride. It's pretty straightforward. Yeah?
How do we lead if we have
An
an iron?
iron at the end?
Like instead of F4 on the board, you put Fe. What do you call it?
Okay, so first of all, you're never going to find a compound like that because iron metals will always come first. Second of all, if it does contain a metal, then what method do we use? Then we use the ionic compound method, right? And if it's something like FeS2, what would this compound be called? What do we call this one? Iron. Okay. Iron. We're confident on that part. What would the N be? Sulfide. Whoops, sulfide. Not sulfate. Or not sulfite, right? But sulfide. And then what goes in here? All right. This business with mono, di, tri, tetra, hexa, hepta, all these, right? This is only for what? Molecular compounds. How do we indicate, or what kind of information do we need to convey when I'm telling somebody that I have a compound that contains iron and sulfur? I just need to let them know the charge that's on that iron in that compound. So what is the charge in this specific condition? What's the charge on the iron here? It has to be a +4 because sulfur makes I can see up there, it has 16 electrons and wants to have 18. It's going to make have a -2 charge in its compounds. And there's 2 of them. So 2 of these -2s, the iron must have a +4. So this is now called iron what sulfide? 4 sulfide. Iron 4 sulfide. Where the 4 is telling me the charge that's on the metal, the transition metal in the ionic compound, right? Okay, so I think we've got that one okay. That one's probably okay. Here's a little table that you can use. It's in the book as well. If you want a little help on trying to identify what the name of a compound is. You know, I doubt if you're going to memorize this. Really, if you just remember what the name of this compound is and the kind of compound that it is and what the names of these 2 compounds are and the kind of compounds they are. Molecular, named one way. ionic named another way. I think that that'll be the safest way to name your compound. Okay, so now last class we briefly mentioned that there's a whole other class about carbon compounds, right? It was called, what's the name of that class? Organic chemistry. Anybody need to take organic chemistry in the future? Not a soul. Oh, maybe somebody needs to take organic chemistry in the future. Okay? It's the study of carbons. But there are a few simple organic compounds that you are already a little bit familiar with, but that you need to kind of know because there will be questions that utilize these more common organic compounds. All right? So we're going to introduce briefly how to name organic compounds. All right, propane. Have you guys heard of propane before? When you go camping, you have those little tanks. Those are propane tanks. Tanks of propane. The big tanks outside houses in rural areas are filled with propane. Okay. This is a gas. It's an organic compound, and prop is a prefix in organic chemistry for 3. I'm going to erase this side now, which is our ionic compound, and we're going to bring up the naming of organic compounds over here. All right? Propane is one that you're familiar with. Prop is 3. Butane. Have you guys heard of butane lighters? Those are the lighters that you use to light your smokes, right? You can see on clear butane lighters that it's a liquid, right? Have you seen that? But then when you hold down the thing, you hold it up to here and you can listen, right? It's letting out the material as a what? As a gas. If you hold it up to a light that's way far away, you can see it's pretty thick gas, right? Because it's right on the edge there of being, if it's pressurized, it's a liquid, but when it comes out as a gas. So that's butane. And that is 4. Propane looks like this. A carbon connected to another carbon, connected to another carbon. So the 3 refers to 3 carbons. Butane, how many carbons in the chain? 4. And then we have pentane, hexane, heptane, octane, nonane, and decane, which are all the prefixes that we talked about over here already. Right? So going from 5 to 10, they're the same prefixes. In organic chemistry, the first one, meth, the second one, eth, prop, and bute, are different. Okay? But we're familiar with this prefix a little bit. Have you guys ever heard of that? Does that sound familiar? Ethanol. Ethanol. Right? Ethanol is 2 carbons with an alcohol group on it, like that. And carbons that don't have anything else around them are always filled with hydrogen until there's 4 bonds to each carbon. So that's an example of where we will have heard the prefix ethanol. Rubbing alcohol. Does anybody know a name for rubbing alcohol? It says on the side of that bottle. Isopropanol. Or isopropyl alcohol. Do you hear a prefix up here in isopropanol? Which prefix is there? The prop, right? So again, it's 3 carbons. The propanol, all, means that there's an alcohol group on it. So isopropanol, which is often abbreviated IPA, isopropyl alcohol, is 2 or 3 carbons. And the iso means that the second carbon is where our alcohol group is, isopropanol. So methane, you guys probably have heard a little bit about methane. It's the energy source that's changed the United States, right? Because we can now pull up a lot of methane out of the ground, and now we're exporting it, right? We had that conversation before. So methane, ethane, propane, and butane meth, eth, prop, and but are our prefixes that we kind of want to, don't spend a whole lot of time, but don't be freaked out when you see them on a test. Okay? Usually it won't be a situation where if you don't know the number, then you can't figure out the problem, but you just don't want to be completely unfamiliar with it. Okay, so that I think is a good enough introduction to our organic chemistry. So let's see if we can name all of these compounds. All right, slide 59. Work with your neighbors and see if you can use the rest of the time here to name all of these compounds. As soon as you got all these named, you can get up and go. Just bring it to me and show me or raise your hand and I'll come by. You don't have a neighbor, you got to get a neighbor. Are any of these organic compounds? No, no organic compounds. So organic compounds are made mostly of carbon and hydrogen. So here, if you have anything else in there, well, we don't need to get into that. But organic compounds are almost always just carbon, hydrogen,